You know that feeling when you're just staring at a piece of tech you paid good money for and this little error box pops up on the
Oh,
screen?
yeah, the dreaded pop-up.
Right, and it's basically telling you, like, no, you can't do that, or this device is locked.
It's incredibly frustrating.
It really is. I mean, you own the hardware, it's sitting right there on your desk, but the software is acting like a bouncer at a club holding a clipboard.
Yeah, and telling you your name just isn't on the list.
Exactly. So today, we're actually going to figure out how to stop treating our tech like these magical black boxes. We're doing a deep dive into a really fascinating stack of technical notes from the Etherham platform put together by Tom Sulzer.
And there's some beautifully detailed technical nuance in these sources.
Oh, absolutely. Our mission today is to arm you with the tools, the workarounds, and, the hacks to just politely ignore that digital bouncer. We're going to trick AI hardware into unlocking its full potential, resurrect supposedly dead radio modems with a $10 wire, and pack our system data so tightly it survives basically any hardware apocalypse.
Sounds like we're moving from being passive consumers to actual active owners.
That's the exact mindset shift we need. So let's jump right into it. A great place to start is, well, one of the most computationally heavy things you can do at home right now, which is running local AI.
Right, keeping everything off the cloud.
Yeah, because if you want true privacy for your data, you have to run those large language models like a llama locally. But finding the hardware for that right now in mid-2026 is a serious hustle.
It's a massive challenge. I mean, for a while, the standard advice in the local AI community was just to go buy an Apple Mac Mini M4.
Specifically the one with 24 gigabytes of memory, right?
Exactly. The 24 gigabyte model handles the workload beautifully. But as we know, there's a severe memory chip shortage going on.
So those 24 gigabyte Mac Minis are essentially unicorns at this point.
Yeah, they really are. If you can even find one in stock, the prices are pushed well over $1,000.
Even the refurbished market is totally dry.
It is. But I think it's really worth understanding why the Mac Mini became the gold standard in the first place, because that actually dictates how we go about building our workaround.
Okay, let's unpack this because it really comes down to the architecture. People usually assume that running a local model is just like a raw compute problem.
Right, they think they just need the fastest processor cores available.
Yeah, but generating tokens is actually a memory bandwidth problem, isn't it?
It absolutely is.
Yeah.
You have to load the model's weights into the processing unit for every single token it generates.
So it's like, think of it like a grocery store checkout. It doesn't really matter how incredibly fast the cashier is.
The cashier being the CPU in this case.
Exactly. If the conveyor belt, which is the memory bandwidth, is moving at a snail's pace, the cashier is just standing there waiting.
That is a perfect analogy. That constant shuffling of billions of parameters is the true bottleneck. And the Mac Mini uses a system-on-a-chip architecture with unified memory.
Meaning the processor and the graphics unit share the exact same physical pool of memory right there on the chip.
Right. So instead of funneling massive amounts of data back and forth across these narrow PCIe lanes to a separate graphics card, that unified memory acts like a massive multi-lane highway.
And that highway is moving at, what, 120 gigabytes per second?
Yep, 120 gigabytes per second, which lets the Mac Mini spit out, 30 to 50 tokens per second on a standard 7 or 8 billion parameter model.
Which is incredibly snappy. But since we basically can't buy that hardware right now, the sources point us to a really compelling workaround.
The AMD Mini PCs.
Yes. Specifically, a unit called the GMK Tech NUCbox K8 Plus. It comes in at around $740.
Which is a huge price difference.
Mm-hmm.
And the hardware specs on that unit are genuinely impressive. It uses an AMD Ryzen 7 845HS processor.
And that has a surprisingly capable integrated GPU, right? The Radeon 780M.
Exactly. Plus, unlike the Apple ecosystem, you can actually open it up and upgrade the DDR5 RAM yourself.
Oh, and we have to mention the Oculink port. That is a massive advantage.
It really is. It means you aren't permanently locked into the graphical compute power you bought on day one. You have this high-speed external interface to just attach a full-size desktop GPU later on if you need to scale up.
Right. But getting the AI software to actually utilize that integrated Radeon chip that requires you to wade into Linux.
Yeah, this is where we have to trade market scarcity for a bit of elbow grease.
Because Apple's Metal integration just works out of the box. But with AMD, you have to use a specific compute stack called ROCm, right?
Right. And ROCm officially targets high-end enterprise server GPUs. It really doesn't want to play nicely natively with a consumer-grade integrated chip like that 780M.
So the sources highlight this very specific environment variable you have to set in Linux before you even launch a llama. It's HSA override SS version 11.0.0.
Yep, that's the one.
So what does that string of numbers actually do under the hood? Like, why are we doing that?
It's essentially a spoofing maneuver. You are forcing the ROCm HIP compiler to treat your consumer chip like it's a supported enterprise architecture.
Oh, wow.
Yeah, so the 11.0 refers to AMD's Navi 31 architecture. The 780M is technically a different subversion, but the instruction sets are close enough.
So if you trick the software into treating it like the higher-end silicon, it'll just compile and run the AI kernel successfully.
Exactly. But if you miss that single line of configuration, the performance drop is brutal.
Yeah, the sources say you plummet from like a really snappy 20-plus tokens per second down to a sluggish 5.
Because the system just gives up and falls back to the CPU. It's literally the difference between having a real-time conversation and, waiting for an old dial-up modem to load an image.
It's crazy that one line of code unlocks all that hardware potential.
It gives you incredible flexibility. And, the principle of bypassing software limitations transitions us perfectly into our next topic.
Right, because sometimes the roadblock isn't missing Linux drivers. Sometimes it's a manufacturer deliberately putting up a brick wall on a device you already own.
Which brings us to this total nightmare scenario in the notes about amateur radio hardware.
Oh yeah, this part was wild. So imagine you have a digital voice modem, specifically an MMDVM dual hat, and it's attached to a Raspberry Pi.
Right.
And you log into your WPSD web interface to just do a routine firmware update. But it throws this terrifying error message. Modem flashing failed. The modem is possibly locked from the vendor.
That phrase, locked from the vendor, is incredibly discouraging.
I'd be furious. Most users see that and just assume the hardware has been permanently disabled or bricked.
Exactly. They just throw up their hands and start shopping for a replacement board.
But the board isn't locked at all, is it?
Not at all. That error message is just a really lazy assumption by the software.
Okay, so what's actually happening when it throws that error?
Well, the standard flash method relies on a serial port connection. Your computer tries to initiate a handshake with a tiny piece of software on the modem's chip called a bootloader.
Right.
But on older boards, or just under certain timing conditions, that handshake simply times out.
Ah, so the flashing software sees the timeout and just defaults to that scary error message claiming it's locked.
Precisely.
Okay, but here's where it gets really interesting and honestly a little intimidating for the average user, because the solution the sources recommend sounds kind of extreme.
You're talking about the ST-Link V2 dongle.
Yeah. They say to buy this $10 USB dongle, then you have to find 4 unpopulated microscopic holes on your modem board labeled GND, CLK, DIO, and 3v3.
Yep, the debug header.
And you actually solder metal header pins directly into those holes and run jumper wires to the dongle. I mean, wait, aren't we essentially doing open heart surgery on the modem at this point?
It definitely sounds intense.
Like, is there a massive risk of just writing corrupted firmware directly to the silicon and bricking it forever?
Well, what's fascinating here is you actually aren't hacking the board at all.
I'm not.
No, you are using the manufacturer's own backdoor. Those 4 pins correspond to a protocol called SWD, or Serial Wire Debug.
Okay.
It's a low-level hardware interface built directly into modern ARM microcontrollers.
Yeah.
This is the exact method the factory used to program the bare silicon before a bootloader even existed.
Oh, so the serial port and the bootloader are just like a software convenience layer that sits on top?
Exactly. And when that convenience layer breaks, we just bypass it entirely.
Yeah.
You communicate directly with the hardware state machine of the chip using a tool called OpenACOD.
But what about the fear of bricking the device?
That's the best part. The SWD interface is incredibly robust. Let's say you initiate the flash over your newly soldered wires, and the process times out halfway through.
Which is the exact moment panic sets in for the average user. Because the board appears completely dead, right? Or no LEDs blink, nothing.
Right, the software is effectively erased. But because you're wired directly into the debug hardware, the state of the software on the chip is irrelevant.
Wait, really?
Yeah, the SWD hardware interface remains awake and listening as long as the chip is receiving physical voltage.
So you just hit the up arrow in your terminal and run the flash command again?
That's it. You literally cannot permanently break the software because your physical wires override everything.
That is amazing. It completely changes how you view a piece of quote-unquote dead electronics.
It gives you the ultimate override switch. But, rescuing your hardware modem is really only half the battle.
Right, because the brains of that entire operation, the Raspberry Pi computer that the modem is attached to, that relies heavily on a micro SD card for its operating system and storage,
And micro SD cards are notoriously volatile.
especially when they're running continuous operations like a radio node. It's not a matter of if the flash memory will degrade and corrupt your custom configuration. It's purely a matter of when.
Exactly. So backing up those cards is absolutely mandatory.
But even the backup process has this massive, frustrating gotcha.
Yeah, the capacity issue. Most people default to using a raw imaging tool, like Win32 Disk Imager.
Which creates a perfect sector-by-sector clone of the microSD card, right? Every single 1 and 0 gets mirrored into a file.
Right. But the capacity labels on those physical cards are basically a lie.
Okay, explain that, because this drives me crazy.
So let's say you perfectly image an 8 GB card. 6 months later, that card dies. You go to the store, buy a brand new 8 GB card, plug it in to restore your backup, and the software flat out refuses to write the image.
Because of manufacturing quirks, like how bad sectors are mapped out at the factory.
Exactly. That new quote-unquote 8 GB card might have just a handful fewer microscopic storage sectors than the card you imaged 6 months ago.
It's like buying an 8-foot rug to replace your old one, but the new one is an eighth of an inch too long for the room. You just can't put it in.
That's it. The sector-by-sector clone tool hits a wall, sees it won't fit perfectly, and panics. It just aborts the process completely.
So what's the workaround? I know some people just brute force it by buying a 16 GB card just to hold an 8 GB backup.
Which works, but it's wasteful. The elegant engineering-grade solution the sources point us to is a free bash script called pshrink.
Written by Drew Bonacera, right?
Yeah.
So pshrink solves the sector mismatch completely. But how is it actually manipulating the image file without destroying the data inside?
It's actually a brilliant piece of Linux administration. The script takes your raw backup image file and mounts it using a Linux loopback device.
Because the image file isn't a physical drive, so the OS has to pretend it is.
Exactly. And once it's mounted, pshrink uses a utility called resize2s to do the math and physically shrink the Xtito file system down.
Oh, so it shrinks it to fit only the actual data stored on it, not the total size of the original card?
Right, so if you only had 2 GB of actual files on that 8 GB card, pshrink rewrites the partition table inside the image to be exactly 2 GB.
Wow. So you can now restore that image onto literally any card that is 2 GB or larger. The tiny manufacturing variations just don't matter anymore?
They're irrelevant. And furthermore, it automatically embeds a flag into the startup sequence of that new image.
Oh, right. So the very first time you boot your Raspberry Pi with the restored card, it triggers an expansion protocol.
Yep, it automatically fills whatever empty space is available on the new physical card, so you maximize your storage without doing anything.
That is so clean. And you can run this script directly on the Pi if you have enough free space, or you can run it through the Windows subsystem for Linux.
The sources also mentioned you can use a gzip compression flag.
Oh, right, adding a little Z in the command.
Yeah, to compress the final file even further. The space savings are substantial, especially if you're archiving dozens of node backups on a network drive.
But there is a catch with that, right?
There is. Raw imaging software like Win32 Disk Imager cannot write a compressed archive directly to a card.
Ah, gotcha. So you have to add an extraction step, like using a tool like 7-zip to decompress the image back to its raw state before writing it.
Exactly. It's an extra step, but totally worth it for the space savings.
For sure. Oh, and real quick, before we move off the Raspberry Pi infrastructure, there is a vital power tip in the notes we should mention.
About the USB battery banks.
Yes. So many people try to build a cheap, uninterruptible power supply for their Pi nodes by just passing the wall power through a standard USB battery bank.
Seems so logical, right? If the wall power cuts out, the battery just seamlessly takes over.
But it is actually a disaster for flash memory.
It is, because standard power banks use battery management systems, or BMS, designed for charging cell phones.
Right. And when the battery drains down to its minimum threshold, the BMS doesn't slowly taper off the voltage to let the computer shut down gracefully.
No, it abruptly cuts the power circuit entirely to protect the lithium cells.
That's a hard kill. And that sudden, ungraceful loss of power is the exact scenario that corrupts the file system on a microSD card in the first place.
You're essentially manufacturing the exact failure you were trying to prevent.
Which is wild. You really have to deeply understand how these components behave under stress.
You do.
And I guess that brings us to the ultimate question driving all of this. Why do we go through all this trouble? I mean, why are we spoofing ROCm software soldering headers onto modems, and meticulously vacuum sealing our data partitions with PishRank.
Well, it all circles back to independence and resilience.
Right.
It's about maintaining your ability to communicate, process data, and coordinate when commercial infrastructure inevitably fails or just becomes unavailable.
The sources ground this in a very real historical event, actually, the May 18th, 1980 eruption of Mount St. Helens.
Yeah. When that blast occurred, it completely decimated the telephone and power infrastructure across southwestern Washington.
And who stepped into that void? The amateur radio operators.
Exactly. They provided emergency communications, coordinated search and rescue operations, and handled liaison traffic for government agencies.
Because they owned and understood their infrastructure from the bare silicon all the way up to the antenna.
Precisely.
And there's this beautifully tragic detail in Tom Salter's notes about this. So Tom is a mining geologist, right?
Okay.
And he spent years totally fascinated by that mountain, but he took a job and moved out of the state literally weeks before it blew up.
Oh man, a painful irony.
He missed the geological event of a lifetime.
That hurts. But, you know, the legacy of those radio operators who responded to that event, it continues to evolve.
Oh, absolutely.
If we connect this to the bigger picture, this whole ethos of resilient, independent technology reaches all the way into low Earth orbit.
Yes. You can literally communicate with the International Space Station using this exact amateur radio technology.
Incredible.
There is a Kenwood D710 GA radio just sitting in the Zvezda service module up there. And if you want to bounce APRS data packets off the space station, you just target 437.825 megahertz on the 70-centimeter UHF band.
But doing so successfully requires a total masterclass in understanding the physical limitations of your hardware.
Because the ISS is moving fast.
Extremely fast,
Right.
roughly 17,500 miles per hour. And at those speeds, on the UHF band, you run into severe Doppler shift.
Right, like how an ambulance siren changes pitch as it drives past you.
Exactly. The radio waves physically compress, which raises the frequency as the station approaches you, and then they stretch out, lowering the frequency as it recedes over the horizon.
So if you just tune your radio to exactly 437.825 and leave it there, your data packets will just bounce off into the void.
Because the relative frequency is constantly drifting.
So how do operators actually compensate for that during like a super narrow 10-minute pass overhead? You can't just sit there trying to manually spin the dial on your radio, right?
No, definitely not. You interface the radio with your DC using a scene control cable.
Oh.
And you run satellite tracking software like gPredict. The software calculates the orbital mechanics in real time and continuously feeds these micro adjustments to your radio's frequency to perfectly counter the Doppler shift.
That is so cool. It requires all your hardware and software to talk to each other flawlessly.
It really is the ultimate payoff of everything we've talked about today.
So what does this all mean for you? We've covered a ton of technical ground today. We started by bypassing $1,000 hardware bottlenecks by spoofing enterprise software drivers on AMD processors.
We broke through artificial software locks by physically wiring into the debugging architecture of our microcontrollers.
And we learned how to manipulate partition tables to ensure our system backups can actually survive hardware failures.
And the common thread running through all of this is agency.
Yes. Consumer electronics manufacturers increasingly want you to view their products as sealed, magical black boxes.
Right. When something goes wrong, the expected consumer behavior is to just throw it away and purchase the newer model.
But the tools we explored today, the ROCm environment variables, the ST-Link V2 dongle, PishRank, these are the tools that pry that black box open.
You don't have to be at the mercy of arbitrary hardware limitations.
Exactly. With some targeted research, a willingness to learn the command line, and maybe a $10 soldering iron, you can truly own your entire technology stack. You can tell that digital bouncer to just step aside.
Devices stop being disposable appliances. They become platforms that you actually control and maintain.
So I want to leave you with a final thought to chew on. We hear a lot of debate right now surrounding the right to repair movement, the legislation dictating that you should be allowed to replace a cracked screen or a dying battery on your smartphone.
Which is important.
Definitely. But what if that movement evolved into a broader right to tinker at the firmware level?
Oh, that raises a massive question about transparency.
Right. Imagine a regulatory landscape where consumer electronics are simply not allowed to hide their debugging architecture. What if, instead of covering up the SWD interface, manufacturers were legally required to include the exact factory flashing tools, the pinout diagrams, and the unencrypted firmware documentation right there in the box when you purchase the device?
It would fundamentally democratize hardware development. I mean,
Yes.
it would massively extend the life cycle of the electronics we produce.
Think about how that level of radical transparency would change your relationship with these seemingly disposable electronics surrounding you right now.
It changes everything.
Next time a piece of technology throws an error and tells you access denied, ask yourself, whose device is this really?